All right, let's cover the third part in our lecture series on C++ functions. Remember, a function is just a group of statements that put together perform a specific task. All right, we're going to briefly discuss procedural abstraction, scope. We'll skip over storage class, go on to overloading function names, how to work with a void return type, and then what call by reference is in this lecture. So procedural abstraction, right? Procedural abstraction is just a term for hiding the way the code in your function is implemented, right? If somebody else wants to use a function that we wrote, all that person needs to know is what the function does, right? But they don't have to know how the code inside accomplishes its task, right? So a typical analogy is this: we have this black box that we can't see into, right? So we can't see into the function to see how the code's working. What we really know about the function is if we look at its declaration and see its parameters, we'll know what sort of arguments to pass to it. We'll have an idea of what action it performs and what, if any, values are returned. That's all we need to know. We don't need to know what's going on inside. That's often called procedural abstraction. A function, some languages call functions procedures, right? C++ calls them functions. It also relates to a term that's often used with C++ is that information hiding, right? That simply emphasizes that the programmer acts as if the body function were hidden from its view. Normally, if you were to give somebody else your libraries to use, what they'd be looking at are perhaps the function declarations and a set of comments, or maybe a set of documentation on how to use them, but they wouldn't want to be looking at your code, right? If it's open source, they can see your code if you share that with them, but if not, if it's a paid product, then they can often only see the function calls, the documentation on how to use your function. Right? In order to allow the programmer to know how to use your function, you have to provide a well-written comment block to let them know how to use it and what actions it performs. Right? So a slide from the book, they just give you an example that here is the function declaration. Remember, when we declare a function, we simply write its heading, its header, right? So its header, remember, has the name of the function, data return type, and then parameter list. And it's followed by a semicolon. That says we're declaring the function to exist. And in this case, the set of comments they wrote after this was returns the balance in a bank account after posting simple interest. The formal parameter, balance par, so balance par. And your book is using par as an ending name for parameters at this point, right? That's not something that you typically see, but the book just wants to emphasize that these are parameters. So balance par is the old balance, right? That's the current bank balance. The formal parameter rate par, well, that's the interest rate. And then we have to know, well, is that interest rate in percentage, right? What form is it in? So they give you an example here, right? If rate par is 5.0, then the interest rate is 5%. And the new balance, so if you call the function new balance, pass it 100 as your current balance, and then 5 is 5%, right? The new balance would be 100 times 1.05, paying you then $5 in interest. So that lets the user know how to use the function, these comments, and the prototype lets them know what arguments they have to pass and what data type they can expect to have returned to them, right? But then they gave you two examples here, right? Here's where one definition of the function. Notice in both definitions of the function, the function heading is the same. What's different is the part inside, right, where they calculate the updated balance somewhat differently. So their point is that the programmer doesn't have to know if you wrote your code this way or that way. The same results occur no matter what. That's what we call procedural abstraction and information hiding. Not something we'll spend a large amount of time on in this course, but you may hear the term. All right. So the next section, this is one of our most important sections in using functions, is scope. Right? So all variables have two attributes. They have scope and a storage class. Scope simply means it's the area of the program where the variable is valid, where you can access it. The global variables are valid from the point where they are declared to the end of a program. And a local variable is limited only to the block in which it's declared. It can't be accessed outside that block. And a block is defined by a section of code enclosed in curly braces. Storage class happens to define the scope, the visibility, and the lifetime of variables and or functions. All right, so scope is important for us. So let's start with this example. In this example, we have both a local and a global variable, right? Notice here then the global variable, I named global to emphasize it. It is declared outside of any set of curly brackets, right? So here I declared it above main. Right? And then here's our main function. Inside, I declared a variable of type int named local, right? It's local to main. No other function, if there were any other function in this program, would be able to see this variable. But global variables can be seen anywhere. So inside main, main can access global, because remember, once global is declared, it's declared right here. Remember, your compiler starts at the top of the file and works downward to see things. So at this point, the compiler would have looked at global and said, oh, okay. When it got here to check the syntax, it would say, I know what global is. So it's legal for main to access the global variable. And so any changes we make to it in main will actually change the memory. So when it's declared out here, we don't know what's stored in its memory, but down here, we can assign 1 to it. Within main, right, we can make changes to local after we've declared it. And then here's something else you can do. Right? You'll sometimes see other blocks of code surrounded by curly brackets. We've seen that with while loops, right, for loops, if statements. And once in a while, someone will declare a variable inside a set of curly brackets. And sometimes people will write this accidentally, but what happens is when you create these curly brackets here, you started a new local block of memory. So in here, where this variable is declared, it comes into existence here. And you can start using it from this point where it's declared all the way until this ending curly brace. And this local area of memory can still see this local variable and the global variable. So this is legal to access it here. Right, we get to the end of this block. Once we get beyond the end of this block, main could still access local and global, but it could no longer access block local because it went out of scope at the end of this curly brackets, right? Its lifetime is ended and we can no longer use it. All right, so those are the differences between global and local. Remember, local variables are usually declared inside of curly brackets here. Global variables are declared outside of sets of curly brackets. Oh. So that's repetitive in terms of scope means the accessibility and visibility of the variables at different points in the program. Right? Variable or constant has 4 types of scope. So block scope, that's inside the curly brackets we've seen. Function scope, well, function scope relates to the parameters in our parameter list. File scope relates to global variables that are in one file. We've only ever seen one file so far. We haven't made multiple file programs. It is possible to create a global variable that's accessible outside the file it's created in. Right? And then program scope, those would be global variables that are accessible from one file to another. Right? We're really only mainly concerned with block and function scope. File scope will be concerned about if we use global constants. And once again, block scope then, to reiterate, is a group of statements enclosed within opening and closing curly brackets. Right, and that's what we saw in this previous example, that in this particular block, we made a variable called block local. It had a scope from its existence here to the end of its life here. Local, when it was declared inside this block of curly brackets, came into existence here. We could use it all the way until we came down to this ending curly bracket where it then goes out of scope or out of existence, right? So that's what we mean by block scope, is that variables that are declared inside a set of curly brackets. So also, variables that are declared inside for loops have a limited lifetime. So let's take a look at this example, right? I've declared a variable here in main called sum. This variable is local to sum. It's declared inside this set of curly brackets. So it's declared here. It comes into existence. We can use it anytime from here down to the end of main. Now in this for loop, I've created a variable called int, right? Notice it was declared here and initialized. So it exists as long as this loop is running and exists. So as long as this condition is true, I exist. So we can see in this particular case, right, when I is equal to 0, 1, and 2, this condition will be true. So this loop will execute. We'll be adding I into the sum. Once this for loop finishes execution, well, when I becomes 3, 3 less than 3 becomes false. So when I becomes 3, this condition becomes false. right? For loop is done. The variable I, since it was declared here inside the for loop, no longer is in existence. So down here, if we were to try to access I, right, the compiler would generate an error saying that I is an undefined. So it gives you I is undefined error. So it's out of scope. Right. So if we needed to use the variable I throughout our entire program, instead of declaring it here in the for loop, we would want to declare it before the for loop outside there, so it would be accessible to the rest of main. So that's a common error that sometimes occurs, right? As you declare something here in the loop, forget about it being local, try to access it later, and you get that error. So function scope. Besides block scope, then function scope is important to us. Parameters are active and visible from the beginning to the end of a function. So here are our parameters. Remember parameters? Here's our parameter list. So in this case, fun A has two parameters, A and B. Right? From the time this function gets called, these variables will come into existence. Right? This local variable, once this function gets called, is declared, initialized. It will stay in existence until the function ends. Right, so let's take a look at the way this program would flow. Remember, programs always start execution with main. So here's our main function. We've declared a variable x, which is local to main, set it equal to 10. So if we were to run this, right, this would print out in main x is 10. And then we call function A. When we call function A, remember we call a function my name, we need to pass it two arguments. Why two? Well, let's look at its prototype, its header. Its parameter list there's two parameters in the list. So with two parameters in the list, we have to have two arguments when we call it. Right? And there's a one-to-one correspondence. So this minus 13 here in this list, this argument will get assigned to A, and the capital Z will get assigned to the char B. Right? So as soon as we call this function, execution, flow of execution transfers up here. A now has a value of minus 13. We say call by value because we call the function and we're passing it this value of minus 13 and this value of Z. B has the value of Z. Right? X is equal to 5. And why am I talking about this in a slide when I should actually just be showing you this in Visual Studio? So let me bring up Visual Studio and let's see. That is example 3. So let's take a look at example 3. I need to exclude these others from the project. Let me clean that. Let's build this. All right. So let's take a look at the flow of execution. All right. So I'm going to put my cursor here in main, and I'm going to right click and say run to cursor. All right. That's going to start the debugger. All right, we'll give it a second to pop things up. So here we are, right, we're in main. So the yellow, remember the yellow arrow indicates the next line of code that's waiting to be executed. Meaning this line of code above is the only one that's been executed. We can see that X was declared, it's local to main. It was assigned the value 10, its data type is in. So this local shows us what the local variables are. But debug menu then, I just want to go ahead and run the cout statement. So I would say step over. I don't want to go into the cout function to see how it works, so step over, right? And the console window is on my other screen. You can see then that cout printed out in main x is 10. So now let's step into the function fun A. So our debug menu, we want to say step into so we can go inside the function. If we were to say step over, it would execute all the code in the function and we wouldn't see it executing line by line. So step into. All right, so you can see our flow of execution went here from fun A up here right now to the first line of fun A. And let's take a look at what our local variables are. So now we see A, B, right, and it's showing X. Now this is not main's X, this is local to here. It's showing this with garbage values. The compiler knows that it's going to be declared, and it's showing up here in the debugger as soon as we execute this line of code. So remember, I'm going to say step over F10, right? And I'm going to hit the F10 key again, right? So that now we can see down here, X was assigned a value of 5. Right, so we can see, as I was saying, now that we're in this function, notice a got a value of minus 13. Well, this expression was assigned to a. This expression z, right, this value, that value was passed to b. So a and b got their values from the function call. X got its value from being assigned. So this also makes the point then that we can have local variables that have the same name in the program, simply because this one is local to this function, right? It does not access this X's memory. They have separate memory spaces. All right, so now if I just say F10 again, right, to step over, let me pop up the console window. Right, in fun A, X is 5. In fun A is minus 13. If I hit F10 again, right, to step over for the next line, I have to make this active, F10, right? It printed out that last one. In fun B, B is Z. Right, so now we can see we're at the end of our function. I'm going to hit F10. Right, and so now we left the end of the function. We come back to in main where the function was called. Right, now you can see that we're back in main. A and B are gone. A and B are completely gone because this function, all of that's been, think of that, it no longer exists in memory. The X that was local to this function is gone, and now we have main's X again, right, which has a value of 10. So F10, right, I hit F10 again to execute that last line. We can see that after calling, well, I need to add a G there, after calling function A in main, X is 10. Right, so that just gives you an idea of how parameters get their values, right? Call by value in this case, how they got assigned their values. It showed you that when you use variables that have the same name, when they're declared locally to inside a group of curly braces, they are in a completely different memory space. So the debugger will help you understand how programs flow and how variables are accessible and not accessible by looking at its memory space. All right, so I'm just going to hit stop debugger there to stop that. And that was the end of that particular example, right? And so that's the same program with the output in the slides, right? Global variables, right? We talked about block scope, we talked about function scope, program scope, global variables, right? If a function wants to access variables that are not passed to them as arguments, one method is to declare variables outside any function blocks. Right, so global variables are declared outside of function blocks. They're not a parameter list, they're not inside curly brackets, and they can be accessed from any point in the program from where this was declared. Right, for its lifetime, it's created at the beginning of program execution. Right, so normally we place all our global variables at the top of a file, and they remain in existence throughout the period of execution of the program, right, until main finishes. Like I said, global variables, normally declare them at the top, not inside a function. Now, we try to give global variables and local variables different names. If we don't, we have a naming conflict. So if a variable declared in a function has the same name as that of the global variable, the function will use the local variable. So think of the local variable always hides access to the global variable and ignore the global variable. Right. I recommend, right, that you don't name local variables the same as any global variables. You'll actually find in C++ programming, we avoid declaring global variables. It's poor programming practice. It can lead to a lot of conflicts. Global constants are okay, but global variables, no, we avoid those. All right, so let's take a look at example 4 here. Exclude example 3. All right, let me clean this and then rebuild. All right. So in this particular program, I've declared a global constant. Right? Global because it's outside of any function, right? It's not in a parameter list. It's not in a set of curly braces. So we have this global constant. Remember, a constant variable is read-only. So when we create it, we have to assign something to it. We can't later write to it. Also created then, in this particular case, a global variable. It's not a constant because it doesn't have the keyword const. Right? As a matter of fact, this global constant may just be up here from a previous example. It doesn't look like I'm actually using it. What's important here in this example is here's the global variable, right? It's not a constant, so x, right? X can be seen from any function. Remember, program execution starts with main, so it wouldn't matter if we had 40 functions above main. If I want to see how a program is going to execute, I always go to main and the first line in main. So here in main, right, if we were to run this and print out global variable x's, well, if this refers to x, notice no x has been declared yet inside main, so the only thing it knows about is the global variable x. So I'm going to put my cursor there, right click and say run to cursor. Right, so what it did was it executed this line of code, right, printed out global variable x is 77, so it's referring to that x. Now we're going to call the function fun_a. We're going to pass it one argument. We're passing it one argument simply because there's only one parameter in the list. Right, the parameter is of data type int, we're passing it an int. So if we go to the debug menu, right, we can say step into F11. Right, so we want to see now how this program executes. Notice here in this parameter list, we have a parameter named x. So this x is going to get past the value of -13. And it's going to be local to this function, so it's going to hide the global variable. It's not referring to this global, it's referring to the local x that exists here in fun_a, which is why I said avoid using the same names, because if you remember what's going on, that's okay, but most people have trouble with this. So here we have to remember that the x is local to this. Anything we do to the x in this function will not affect global x because that's been hidden from view by the local. All right, so F10, right, in fun_a parameter x is, right, let's pop that up. So we can see that line executed parameter x is -13. I'm just going to make a change to x here. So here F10, execute that line of code. Now we can see the local x is now -26. F10 again, execute that line. When we print that out, right, in fun_a parameter x is now -26. As our program flow of execution leaves this function, so F10, and we go back to main, right, we go back to where we came from. Right. Notice there are no locals in main, right? No local variables have been declared. Autos, our global x is showing over here in autos, right? But in locals, there's nothing that's local to main. All right, so F10 now, right? That finished, and we're going to print out the value of x. So F10 again. Right, let me pop up console. And we can see back in main, when we refer to x, we're referring to the global variable, that value of 77. Right? So that's why it can be confusing to use the same name for local and global variables. Like I said, most of the time, we avoid using global variables unless there's no way around it, and there's almost always a way around it in C++. Global constants are good, they're fine. Global variables themselves are considered to be poor programming practice. Right? Unless there's absolutely, positively no way you can do it without that. All right. So that's the end of global variables. All right, that's our same example. Like I said, this one shows you, once again, the global constants are fine. We declare them outside of any function. The note here, like I just said, global variables, there's rarely ever any need to use a global variable. They make programs harder to understand and maintain. Right? When you work with just your single programming file right now, it doesn't seem that difficult for you to understand and maintain it. But if you think about all of the libraries that are in C++, the few that you've seen, you've not seen most of them. If they all had everything named as global variables, and we named some of our variables the same name as those global variables, and we were depending on something like, say, pi that would already be defined, we might accidentally then not refer to the constants in some of the other globals that we want. Especially, so constants we can't write over, remember globals, non-constants we can. When you have a lot of files, they're very difficult to debug, so we avoid them. We won't talk about static in here. That's beyond our understanding at this point. Storage class, we really don't want to spend time on storage class. What the storage class does is it determines what part of memory where storage space is allocated. We haven't studied the C++ memory model yet. You've heard of RAM before, random access memory. As your program is running, right, your program is pulled into RAM, your data is pulled into RAM while it's running. And so the storage class basically specifies how long the storage allocation will continue to exist. It can also specify the scope as well, whether it has external linkage to other programs. So these are things we've not talked about computer architecture, and we don't in this course, so we won't spend time on this. About the only other thing I want to say about this is the storage class that we use is automatic, meaning memory is automatically allocated for us. We do not have to worry about that. A very simplified model of the C++ memory is there's something called the heap. We've not gotten to the heap. There's an area for global or static variables that they're stored in memory. Your program source code goes into another area of memory. All of the variables we've been creating go into something called the stack. Later in the semester, we'll study a data structure called the stack, so you'll know how that works. But for now, we just know that our local variables are all going into the stack, and they have their own separate memory address locations. Later, we will study pointers and get to know a little bit more about what's going on in the stack. But for now, we really don't need to understand anything else that's going on in storage class. Right. So let's just go on to the next section, right, which is on overloading function names. So overloading function names means that we can give two or more functions the same name. Right? The function definitions have to have a different number of formal parameters, so a different number of parameters in the parameter list, or some of the formal parameters have to be of different types, and or. So here are some examples. So we could create fun A. Here's its parameter list. It has two parameters of type double. Well, we could also create fun A that has two parameters of type int. And we could also create fun A that has one parameter of type int. So notice here, right, same name, different types. Same name, different types. This is all legal. Same name, only one parameter in the list. Right, so the compiler uses the function definition whose number of formal parameters and types of formal parameters match the arguments of the function call. Right, if we called fun A and we were passing one integer argument, then the compiler would know to use this function. If we called fun A and passed two integer arguments, then the compiler would say, I need to use this version of fun A. Right? If we called fun A and had two doubles as the arguments, then it would use this version. Right? So different number of formal parameters, or some of the formal parameters may be of different types. Notice, right, these both had two, but the parameters were of different types. Different number of formal parameters between those two. Right? Back to using the sine function, right? We had a homework where we used the sine function, and back when we tried to look up the reference information for that, we saw that there were 4 different functions named sine. Well, they're overloaded. Notice this one has a parameter of type double, this one has a parameter of type float, this one has a parameter of type long double, and this is related to a template class, which is beyond our discussion at this point. This is just an example, though, of how the compiler knows which one to call. Right? If you call the sine function and pass it an argument of type double, it's going to use this function and return an argument of type double. Right? If you call the sine function and pass it a float, it's going to use this function and return a float. Right? That's what we mean by overloaded function names. When you overload, it can't distinguish by return type. Right? So let's take a look at these two examples of fun A. Notice that they both have the same number of parameters. They both have 2 parameters. They're both of type int. The name does not matter. Right? The compiler really pretty much ignores the name in the function declaration. So if you were to try to overload this and just distinguish between the return types, the compiler would not understand that. It would not know which one of these to use, right? If you think about it, if you call fun A and pass it 2 ints, the compiler really doesn't know whether it should return an int or a double. Even if you're assigning things to an int or a double, the compiler will not be able to decide which one to use. Right, so overloading cannot differ by return type. That's illegal. You'll get a compiler error. Finally then, right, void return type. Sometimes our functions don't return information. Right, so suppose we have a function where we just wanted to print something out. So in this case, here's this function called display menu. It doesn't even have any parameters, so we could leave the list empty, or I tend to put void in there to indicate that the parameter list is supposed to be empty. What this function does is, you can see, it simply displays or prints out using the cout operator this particular menu. Here's an example of the output here. That's its only job, is to output this information. It doesn't do any calculations. It needs to return any information. So in that case, when it doesn't return information, void is the return type. When the return type is void, we don't have to have a return statement at the end of our function. Right. That's what this box is telling you. If you want to add a return followed by a semicolon at the end of a void function, that's fine. I'll see people do that once in a while. For the most part, people don't code that return statement. That's up to you. Right, if it helps you to understand that, then do that. And notice then when we call the function display menu, because the parameter list is empty, we just call it with an empty set of parentheses. Right? It doesn't return anything, so we don't have anything to assign to anything. We just simply call it. And if you were to run this, right, it would just display your menu to the screen. Call by reference, right? So everything we've done before, call by value, means that we have passed expressions or numerical values to parameters. So whenever we call a function, right, the function parameters receive a copy of the value stored in the argument variables. So let's take an example here. We're going to write a function that switches the values stored in variables A and B. After the function finishes execution, the value originally stored in A will now be stored in B. The value originally stored in B will now be stored in A. So they're just going to switch places. Right. So swap function, and this is a call by value example. All right. So here, the swap function, name of the function, it doesn't return anything. It has two parameters, A and B. Here's main. Let's take a look at main now. In main, I declare then two variables, both of type int, A and B. So A has 3, B has 5 assigned to it. And let me just go, I'll go to the next page in a second. Right, we're going to print out in main what the values of A and B are. We're going to call swap. Right, so when we call the swap function, right, when we call that from main, mains A has a value of 3, mains B has a value of 5. I could have called these with different variable names, doesn't matter. What's going to happen is this value of 3 is going to get passed to the A here. The value stored in this variable B here, 5, will get passed to this variable B. Right. So up here in swap now, right, A has 3, B has 5. A local variable is declared. And so at the start of the swap function, if we were to print out A and B, start a swap, A is 3, B is 5. And now if we just store what's in B in the temporary variable, take what's in A, overwrite it in B, and then take what's in temp and overwrite it in A, at the end of the swap function, we can see that A now has the value of 5 and B has the value of 3. This just got a copy of what's in mains A and B, right? Because when we go back to main, right, when the function returns and goes back to main and executes this statement here, after calling this function, we can see that A and B in main are still the same. Right, so pass by value means this function only got a copy of what was in mains A and B. It didn't have access to mains variables. Right, that's call by value. Call by reference then, right, is different. A reference parameter is marked with an ampersand, right, that's added to the end of the type name. So this looks very much like the swap function, same name, same return type, two parameters. Parameter names are the same, but we have this reference operator. The reference operator is going to mean that these parameters have access to memory outside this function. They'll be given access to memory of whatever argument is used in this list to call this. Right? So instead of receiving a copy of the calling argument's function, the function receives access to the calling function's memory. We'll see that reference parameters may serve as input, output, input or both input and output, right? Call by value parameters only ever work as input. All right, so here's the same code again. The only difference is highlighted in blue, right? The parameters are now called by reference. So same thing. Execution starts here in main. A is 3, B is 5. We're going to print this out. We're going to say that A is 3 and B is 5. And then we're going to call swap. So notice when we call swap, the function call is the same as before. We just give it the name of the variables. But instead of the value 3 being passed to this variable has a reference or access to this A's memory space. And this B has access to this B's memory space. Meaning when you have access to memory space, if you write something new to memory, you will affect then the values, the memory values here in main. And so let's look at the next slide where we look at the swap function. So when we call this function now, and this A has access to A's memory, this B has access to main's B, right? Then we still declare the variable temp right at the start of swap. If we still refer to A and B by name, right, we still have 3 and 5. So what happens is when we refer to B by name here, what happens is it basically goes to where main's B is and looks up what's stored in that memory. Right, same way we refer to A here, it goes to where main's A is. Not because we named them A, simply because the first variable in this argument list then gets the address of that variable. And then this gets the address of B, not because the names are the same, because they're given a reference to. If these were called X and Y, if this was X, this was Y, right? When this had a reference, it would still have a reference back to this one's memory. All right, so back in here now, like I said, they're referring to this one's memory. So we're swapping values. At the end of swap, here in this function, we can see that A is 5 and B is 3. When this function ends, and flow of control goes back here in main, and this line of code is executed, you can see now back here in main, we changed the value that was in A and B's memory. So the reference means you have access to variables or memory space outside your function. Right, so that's the difference between the two. Call by value just gets a copy of the value stored in there. Right, this then gives you access to the other's memory space. So you can read from it, but you can also write to it. And if you write to it, right, it has an effect outside this function. And that comes in handy because, as we've seen so far, we've had return statements. And a return statement's only ever can return one value or one object. Right? And if we had multiple things we needed to return or output from a function, we could use reference parameters to serve as the output. Right? Basically, right here, these served as input in terms of they gave the numbers 3 and 5 that were stored in main. They also served as output as we swapped them when we went back, right? Main's A and B were changed. So this was a case where they're both input and output. Here's an example where these may just be output. So we have this function called get2ints. Notice it doesn't return anything, but it has 2 call by reference parameters. We know they're called by reference parameters because we're using the ampersand here after the data type. And so whatever we do to num1 and num2 will affect memory space. If we write, will affect memory space outside here. Right. So back here in main, notice we've got 2 variables, x and y. We call the function get2ints, and we pass x and y to that. So up here, num1, that's like an alias for x. That has access to x's memory space. Num2, you can think of that as an alias for y. Num2 now has access to y's memory space. We prompt the user to enter 2 numbers. In this example, type 19 and -7. So num1 gets the value of 19 stored in it. Num2 gets the value of -7. When this function ends and we go back here to main, well, because these are reference, we affected then what was stored in x and y here. And you can see then back here in main, x now has a value of 19. Y has a value of -7. So that's the difference. Reference parameters can affect, they have a reference to area of memory outside the function. Right. We'll see in later cases when we have objects and we get into more object-oriented programming, where it's appropriate to use these references. For the most part, right now we're going to use call by value. Like I said, the book introduces them at this point, so we'll make their effect known, but we will use them much more later in the course. Other thing being then, your book talks about the types of comments that need to be made. So this book says it prefers that you give a precondition and a postcondition whenever you have call by reference variables. Right? So the precondition states what is assumed to be true when the function is called. The postcondition describes the effect of the function call, states what will be true after the function has executed, right, in a situation which the precondition is true. So if we were to write these for the swap values function, well, our precondition would be that A and B have already been given values, right? Because we want to trade, we want to switch places. And if A and B don't have values or they have garbage in them, switching them doesn't do much good. So we tell the user that A and B should already have been given values, right? Meaning they're going to act as inputs to this function. The postcondition is when the function finishes execution, the values of A and B have been interchanged, right? So we tell the user that there will be an effect on whatever area of memory this points to, right? So preconditions and postconditions in the comments to let the user know if there are effects to the memory. All right, that's it for part 3 of our function lectures.